So this is evidence of evolution, looking at evidence that whales had legs as part of evolution. So we're going to start with homologous traits. And these are traits that no longer have the same function, but they have the same structure. So we can see here that the fin of the whale and the hand of the person do not have the same function. We use our hands for grasping, whales use their fins for swimming, but they have the same bone structure because they come from the same common ancestor. So right here I'm going to write for homologous traits. Oh, I don't want to use the big one. So I'm going to write right here that these are traits that may no longer have the same function, but they have the same structure. And this tells us that they share a common ancestor that had that common structure. So I also want to look at vestigial structure. So right here, this whale has a pelvic bone that's vestigial. Sometimes they also can have femurs. But vestigial structures are those which no longer have a function in the body. So they no longer have a function. So for example, having a pelvic bone as a vestigial structure is evidence they once had legs. So it wouldn't exist if there was not at one point a purpose for it, even if it no longer has that purpose today. So let's also go over here and take a look at DNA evidence. We all know this is my favorite type of evidence. So we have DNA evidence. I can talk about this one all day. Okay. So we looked at the number of nucleotides that are different between species, looking at a specific gene, and that indicates how related they are. The fewer the differences, the closer the relationship. So the number of nucleotides, remember that's a number sign, not just a hashtag. So if you were far apart in terms of relationship, you should have many more differences in your nucleotides. So fewer. So we know that the more time there is when organisms had last shared a common ancestor, the more chances there are for random mutations to pop up, and that's where we're going to get differences in our DNA. So these are random mutations, generally. And we know approximately the rate at which random mutations appear, so we can use that to work back to how close organisms might be. So now we have embryology. How can we use embryonic development to show species relationships? So let's change our color here. Let's go with like an orangey color. So when we look at the human and the whale, we have some similarities. So the whale has nostrils. They're right here on the front. When they're in their embryonic stage, it also has hind limbs. And these are things we also see here in the person. And we see nostrils over here on the person. So early embryonic development can show us many similarities between species, indicating that they also had a common ancestor. And it's important to note that whales had hind limbs as embryos, which means at one point in their evolution, they came from something that did have hind legs. So we see the similarities between species, indicating a common ancestor. And we can use this to build what's called a cladogram, to work backwards to figure out where that point was where they no longer had a common ancestor. So as an embryo, we see that whales had hind legs. So I'm going to add a little bit here between, let's go fossil. I'm going to do the fossils first, then I'll come back and add something between that kind of links the fossil record with the evolutionary embryonic record. So when we look at the fossil record, we found an ankle bone that we looked at from Pachycetus. We found the shape of an ankle bone from Pachycetus. Shows a lot of resemblance to the ankle bone that is found. To that found in two-toed ungulates. And ungulates is the word we use for hoofed mammals. So, examples of two-toed ungulates would be hippos, cows, and camels. Furthermore, in Pachycetus, going on to additional fossil evidence is something specific about their ear. So the early land-dwelling ancestor again, Pachycetus, has a special bone in the ear that is only found in modern whales. So it allowed these whale ancestors to begin to develop underwater hearing. So we know Pachycetus did not have excellent underwater hearing, but it could hear somewhat underwater, and that is what gave it the evolutionary advantage to keep developing. So this brings me to my last point, linking here between the evolutionary evidence of the fossil record and also embryological evidence, is that following the embryological development, in the whale follows that what we see as we track the whale's ancestry through the fossil record. It mimics what we see. So at an early stage, the embryos have hind legs, their nostrils are on the front of their face, just like we see in the early whale ancestors, and then through time that hind limb gets reabsorbed and the nostrils move up further in the head to become the blowhole. Both have hind limbs and nostrils that gradually move to the top of the face. So a lot of different pieces of evidence that we can use here to know that once they had legs, so we know that they came from a common ancestor that had legs, and we can use that to deduce based upon combining all these pieces of evidence, particularly my favorite evidence, the DNA evidence, that their closest living relative is the hippo. Obviously, when I say whales, I'm including cetaceans as a whole, which would include the whales, the dolphins, and the porpoises. So it's the closest living relative. That's important. So we have our hippo, closest living relative. And here is a sampling of the different kinds of evidences that we can use to prove this point.